Hello everyone, I am Prasanna and welcome to this new video. Today we are going to start with the very basics of 8086 microprocessor. This video is especially for beginners, for those of you who are starting your journey with 8086 and want a strong conceptual foundation. In this lecture, I am going to explain the buses of 8086, address bus, data bus, control bus in detail and how the size of each bus affects memory size, data transfer speed and processor performance. Also, I am going to tell you how memory read, memory write, IO read and IO write operations actually work. Why 8086 can access only 1 MB of memory. Where does this 1 MB comes from? What decides it? And also I am going to tell the difference between the 8086 and 8088 microprocessor. And most importantly, two golden rules of memory that will save you from confusion throughout the entire course. So these things I am going to cover in this video. Before getting into the lecture, let me ask you one thing. When you buy a phone, you see something like 64 GB internal memory, which can be expandable up to 256 gigabytes or 1 gigabytes. Have you ever asked why only up to that limit? What decides it? The answer lies in the size of the address bus, and that's exactly what we are going to understand today. The 8086 has 20 bits of address bus. That means 20 address lines. Now here is the core idea. Memory size depends directly on the number of address lines. Let us start simple. A 1-bit address bus means only one line. So the possible values are 0 or 1. This means only we can access two memory locations. That is, there are only two memory locations. If we go for 2-bit address bus, then the possible combinations are 0, 0, 0, 1, 1, 0 and 1, 1. So we are having 4 memory locations in 2-bit address bus. If we go for 3-bit address bus, then we have 8 possible addresses, that is 8 memory locations. So the general rule is, if a processor has n bit address bus, it can access 2 to the power n memory location, and the very important golden rule is one memory location stores exactly 1 byte of data. That is, one location is equal to 1 byte, that is equal to 8 bits. This rule is universal. This rule is universal. It fit for 8085, 8086, 8386, Pentium or any processors you study. Now you apply the rule. If we have 16 locations, then it is of 16 bytes. If we have 256 location, then it is of 256 bytes. Let me ask you a question now. If I have a 16-bit number, how many memory location do I need? Correct, 2 locations, because one location can store only 8 bits. 16 bits is equal to 2 bytes. Finally, the memory size formula is memory size is equal to 2 to the power n bytes. So apply this to 8086. So 8086 has 20 bits of address bus. So the memory size is 2 to the power 20. That is equal to, we know that 2 to the power 10 is of 1 kilobytes. So 2 to the power 20 is equal to 1 MB. So finally we come to a conclusion that the 8086 can access 1 MB of memory since it has 20 address lines. Next, let us talk about the data bus, the speed decider. Memory size tells how much you can access. Data bus tells how fast you can access it. In 8086, we have 16-bit data bus. That means it can transfer 16 bits in one cycle. Let us compare the speed of 8085 microprocessor with 8086 microprocessor. So 8085 it has 8-bit data bus. So it needs 2 cycles for getting the 16-bit data from memory. But in 8086 it needs only 1 cycle. So double the speed. 8086 is of double the speed of 8085 microprocessor. Let us now discuss the difference between 8086 versus 8088 microprocessor. 8088 microprocessor is a lower version of 8086 microprocessor. Both the 8086 and 8088 microprocessor has 20 bits of address bus, but the difference that comes here is of in 8088 we have only 8 bits of data bus. So we can access only 8 bit of data at an instant of time, whereas in 8086 we can access 16 bits of data in an instant of time. So coming to the speed, you all know that since we can access 16 bits of data in 8086 microprocessor, obviously the speed of 8086 microprocessor is of faster comparing to that of 8088 microprocessor. The instruction set for both the 8086 and 8088 microprocessor are exactly the same. The only difference is the data bus. Okay. Now let us talk about the ALU, and also I will clear why 8086 processor is being called as a 16-bit processor. In 8086 we have 16-bit ALU. That means we can add, subtract, multiply, divide 16-bit numbers in one instruction. This is why we call 8086 as a 16-bit processor. This is the first question in most vivas. Now let us discuss on the control bus. Who decide what operation is to be performed? Control bus contains signals, not bits. The three most important signals are read, write, memory and I/O operations. The active low signal indicates the signal is active when it is 0. The bar means active low. The bar which is being indicated here means active low. The 4 basic operations each computer do is memory read, memory write, I/O read and I/O write. The real life example of opening a file is of memory read. Saving a file is memory write. Keyboard input, typing something in keyboard as of I/O read. Displaying or hearing some sound from a speaker is of I/O write. The control signal table is being shown here, right? So if the processor wants to read something from the memory, since I/O is of I/O bar, so the I/O operation, if the processor wants to make a I/O operation, this I/O signal must go low. Here it is of 1 and the read bar signal it is of 0. So read operation will take place. Write is also of active low signal. Here it is of 1. So no write operation takes place. So if a 1 is in memory / IO means then it is of memory. It indicates memory related operation. As the RD bar signal goes low, it indicates the read operation. So it is of memory read. Next, if you go for memory write, then the read signal has to go high and the write signal should be active low in order to initiate the write operation. Okay, for memory related thing. If it is of IO read, then IO read or IO write, then this particular signal M/IO bar must be active low, because in order to make IO related operation, since it is mentioned as IO bar, active low signal must come there. So if a 0 is there, then it is going to indicate IO related operation. If read bar is of 0, then it is of IO read. If write bar is of 0, then it is of IO write operation. Let us now discuss about the memory organization of 8086. The total memory in 8086 is of 1 MB. The address ranges from 5 zeros, that is minimum addresses of 5 zeros, and the maximum addresses of FFFFF in hexadecimal. We are representing the 20-bit address in hexadecimal with 5 bits. Okay. So suppose if I want to store a 16-bit number 1234, right? This is a 16-bit number. I wish to store this 1234 16-bit number in the memory location. How to store it? Already we have discussed that a memory location can accommodate only 8 bits of data or 1 byte of data. Here we have to store the 16-bit number, right? So in order to store it, we are having a golden rule, that is nothing but of little endian rule. According to little endian rule, the lower byte is stored in the lower address and the higher byte is stored in the higher address. In our case, if we want to store this 1, 2, 3, 4 in memory location, the lower number is nothing but of 34. This 34 will be stored in the location 0, 0, 0, 0, 0, and this 1, 2 will be stored in the address location, the consecutive address location, that is 0, 0, 0, 0, 1. Okay. So this rule is followed by all Intel processors, all the Intel microcontrollers. Coming to the summary, in this video lecture we have discussed that the 8086 microprocessor has 20-bit address bus and 1 MB of memory, 16-bit data bus which is going to foster the operation, 16-bit ALU, so what we call it as a 16-bit processor. One memory location is equal to 1 byte. Multi-byte data follows little endian rule, and the control signal decides memory versus IO operation as well as read versus write operation. So if you understand this lecture clearly, everything that follows, addressing modes, instructions, programming, will feel easy and logical. Wish you all the very best and enjoy learning 8086.